We're going to have a look at how we can calculate enthalpy change by doing an experiment. Now, the experiment is specific to the type of enthalpy change we're trying to find. So, for example, enthalpy change of combustion will have its own experiment, enthalpy change of neutralization will have its own experiment, and so on. But the equation for them is pretty generic, and that's what I'm going to run through in this video. And then in later videos, we're going to have a look at how we can calculate the enthalpy change for specific types of reactions. So let's have a look at how we can calculate enthalpy change. Now, in order to calculate enthalpy change, the first thing we need to do is calculate the energy change. So the equation for calculating energy change starts off with Q. So Q is our energy change. And energy, as we know, the units are going to be joules. So when we calculate our answer here, it is going to be in joules, which is notated with a capital J. The equation for calculating energy change is M times C times delta T. And you may have come across this equation at GCSE, you may not have. So running through each part of this equation, the M here is the mass of surroundings. And this is usually going to be in grams. And it's very important to know what we mean by the surroundings, okay? Because you may have quite a few different mass readings. It's important to know that the surroundings in the experiment are going to be where your thermometer is. So if your thermometer is in a can of water, you need to get the mass of the can of water, of the water, not the can. And if it's in a solution, you then need to work out the mass of the solution. Okay, so mass of the surroundings is where your thermometer is. It's also worth knowing that if you have, for example, if your thermometer is in water and you have 100 centimeters cubed of water, it is worth knowing that 1 centimeter cubed of water equals 1 gram. So that means if you have 100 centimeters cubed of water, that is going to equal 100 grams. The C over here is what we call the specific heat capacity. And the units for specific heat capacity are joules per gram per Kelvin. If you haven't come across specific heat capacity before, each material has its own specific heat capacity. So for example, water has its own value, butane has its own value, and so on. And the specific heat capacity is essentially the energy required to raise the temperature of 1 gram of a substance by 1 Kelvin. And the specific heat capacity of water is given to you in the data sheet, because it will usually be of water, or they may say, assume that the specific heat capacity of this solution is the same as water. And the value for the specific heat capacity of water is 4.18. And as I said, that's given to you in the exam paper, in the data sheet. And delta T means the change in temperature. So during the experiment, how much does the temperature change by? It's also worth noting that the temperature can go up or it can go down. And essentially, to work out the change in temperature, you do the final temperature minus the initial temperature. Now, in terms of units, in chemistry, we tend to convert everything automatically to Kelvin. In this case, because you are working out the change in temperature, or the difference in temperature, it doesn't actually matter whether you do this in Kelvin or you do this in degrees Celsius. Because if you increase something by 1 Kelvin, it also increases by 1 degree Celsius. So the intervals are the same. So if I just run through kind of example of that, if I have a initial temperature reading of 0 degrees Celsius and the final temperature reading is 10 degrees Celsius, my delta T here works out as 10 degrees Celsius. If I converted these to Kelvin, so to convert to Kelvin, I add 273. So this one's going to be 273 Kelvin. This one is going to be 283 Kelvin. The temperature difference here, so between these two, is still 10. okay? So because we're working out the change in temperature, you don't have to waste time converting degrees Celsius to Kelvin, okay? You could just do it directly in degrees Celsius because you're just working out the difference between the two. Okay, so if we plug all those numbers in, we then get our Q, which is our energy change. We still haven't got to our enthalpy change, because as we know, enthalpy change must be in kilojoules per mole. Okay, at the moment we have an answer, so our Q is in joules. So we need to somehow get from our joules to kilojoules per mole. So the first thing we're going to do is we're going to convert this into kilojoules. So to go from joules to kilojoules, we divide by 1,000. So that Q value that we've just got from that first equation, we divide by 1,000, and then we have our answer. We still have energy change, but it's now in kilojoules. And to get to our enthalpy change, we're going to take our Q in kilojoules and we're going to divide it by the moles of the substance. Now this is going to be specific to the type of experiment you're doing. So as I do further videos, you're going to see how we can find out the moles. But essentially this is how we get our enthalpy change. And as you can see, the units for this are going to be kilojoules per mole. Now, you think at this point you've got to the final answer, but there's one more thing that you need to do, is you need to decide the sign of your enthalpy change. So looking at the temperature change, if your temperature during the experiment increased, that tells you it's an exothermic reaction, and therefore your value here needs to have a negative sign. If your temperature decreased, that tells you it's an endothermic reaction, and therefore you need to have a positive value for your delta H. And that tends to be what people forget because it's the final step. Once you've done your calculation, you think that's it. But if you're calculating enthalpy change via an experiment, you yourself in the final step have to decide what the sign of the enthalpy change is by looking at the temperature change.